Okay, so we are starting our next unit for today. We're going to talk about domain and continuity. Okay, domain, when we talk about domain, we are talking about all of the possible input values for a function. Okay, all of the input values. Usually when I'm looking at a function, I'm talking about what values can x take? What values can I have for x? And then when we talk about continuity, which we'll get to in a minute, we're talking about, is this function continuous, or are there places where my function is chugging along just fine and then something strange happens? Okay. But we're going to start with domain. And for today, we're going to focus on domain and continuity when I have the graph of a function. Later on, we'll talk about domain and continuity when I just have the function itself. But for today, we're going to work from the graph. So we're talking about input values. What input values are okay? Input would be our x values. What is okay on the x-axis when I'm looking at a graph? So for example 1 here, part A, where I'm looking at what could be the domain of this function, we have what's called a discrete function here, meaning we have a place where it starts and a place where it stops. We'll talk about infinite functions a little bit later on, but the graph that we have here is discrete because we have a defined start point and a defined stop point. So for a situation like this, we're looking at what's the x value farthest to the left and what's the x value farthest to the right. Where do I start and where do I stop? Okay. So x value where I start would be -11. X value where I stop would be +11. And then when we're talking about domain, we need to be very careful with what values we are including and what values we are not including. So do we see here how at -11, we have our smallest x value, we have an open circle? Okay. If it's an open circle, do I actually get to use -11 as a value? No. So for we're going to talk about two types of notation today. For our what's called interval notation, that means we would use a parenthesis here. That parenthesis means we get so close to -11, but -11 itself is not allowed. Okay. On the right end of our function, the greatest x value that we can have is +11. And then do we see how we have a closed circle or a filled in circle at +11? Okay. So can I use +11? Yes. If I can achieve that value, if I can use that value in the domain, then we use a bracket. So that's called interval notation. Small, comma, big, and then you decide parentheses or brackets based on, are these values included in the domain or not? So we're looking for things like open circles or closed circles. The other notation that I'm going to use as we work through our domain problems in this unit looks more like an inequality. So I would say -11 is less than x is less than or equal to 11. Meaning my x values are between -11, but not including it, and +11, including +11, since I've got that or equal to sign there. I'm using both of these notations because I want you to see and be familiar with both. If you go on to take AP Calc, you can expect to see this sort of inequality notation used in the questions that you are given. You can also expect to see interval notation used in the multiple choice section as your answer choices or the way that College Board would want you to give your responses. So with that in mind, thinking ahead, I know that's a couple years for many of us, but with that in mind, I'm going to work in both notations for today. I'm going to show you both that way you get used to both. When you are giving me an answer, unless I specify one or the other, I will take either. Okay, so if I don't specify, give me the domain and interval notation, then you can give me interval or inequality notation. But I want you to practice, be familiar with both. For B, same idea. What's the smallest x value that I can have here for this function? Smallest x value. We're back here somewhere. looks like we're at -6, I think. So -6. What's the biggest x value I can have? 11. So -6 to 11. Parenthesis or bracket on -6. Parenthesis, it's an open circle. How about on 11, parenthesis or bracket? Parenthesis again. So there's interval notation. Inequality notation would look like -6 is less than x is less than 11. For C, I've got something that is not a discrete domain here. Not a discrete domain because I have an arrow on the end here. And the same for D, we've got arrows on the end here, meaning our function's going to continue forever. So if I see arrows, it's going forever. It doesn't stop at that point, it continues on. For C, the smallest x value I can have if we go forever, anybody have ideas on what that would be? My smallest x value? Negative infinity. If we're going to go forever in the negative x's, that would be negative infinity. So my interval would start at negative infinity. And then what's the biggest x value I can have? What's the farthest I go to the right? 4. So my interval would be negative infinity to 4. Parenthesis or bracket on the negative infinity side? Parenthesis. Infinity is always a parenthesis because can I actually like put my finger on infinity on a number line or on an axis? If I just like if I'm on Desmos and I have it graphed or I'm on my calculator, can I like scroll far enough and eventually see infinity? No, right? Infinity is an idea. It's not like an actual value. So because there is no greatest, or I should say least point here, there is no point that is farthest to the left. It just goes forever. That's not a place that I can actually put my finger on. That's a parenthesis. How about on 4, parenthesis or bracket there? This would be a bracket. It's not as sort of obvious of a close point. It's not as sort of like bolded as what we saw there. But if I don't see an open circle, that means I include that value. In inequality notation, we could write this as negative infinity is less than x is less than or equal to 4. Or I could write this just as x is less than or equal to 4. X is less than or equal to 4 means all the values less than 4. So I don't actually have to write this part of it. That doesn't mean you wouldn't maybe see that written a couple years from now on the AP test, but these would be equivalent. Those mean the same thing. D is a little bit different. What makes D unique here? This is one function. Yeah, so I've got sort of two pieces here, and we're going infinitely this way and infinitely this way, but there's a big chunk missing out of the middle, right? There's a big gap, as you said, okay? So I'm going to write each piece. So for this piece right here, my lower bound for my domain would be negative infinity and parentheses, because infinity is always a parenthesis. And then what's my upper bound for this section of my graph? This part of my domain. This piece goes forever back until we hit -4. And since we can actually attain that value, bracket there. And then for my other piece here, we have this big gap, and then we pick up where? We pick up when x is 8. Since I actually have a point at 8, I'll use a bracket there. And then I keep going until infinity. And since it's infinity, we use a parenthesis. When you have a domain that's sort of in sections like this one is, we've got this piece here, and then we have a big gap, and then we've got another piece over here. You might see a little like union symbol here, meaning this part and this part. This is something that if we get to set notation, which I don't know that we will this year, but at some point if you were in a class that talks about set theory and set notation. That's something you would see in there a lot. Another way that we could represent this with our inequalities would be this part I could represent as x is less than or equal to -4, and this piece x is greater than or equal to 8. Again, with that same notation in the middle. Questions for me so far? Okay, on the next page. We've got a graph here, a discrete graph, because again, we're not continuing forever in any direction. Go ahead and evaluate f of -3 for me. What's f of -3? Back to our unit 1 function notation evaluating there. F of -3 means I go to where x is -3 and we find that point on the graph. It's -1. How about f of 3? I got nothing there, right? I have 2 open circles there. So I would say that this value is undefined for my function. I don't have a closed point when x is 3, undefined. So if I talk about the domain of this function, can we agree that our domain would start at -5? And can we agree that our domain would end at 6? Okay. Do I take every value in between -5 and 6? Everything in between those two values is part of the domain? I've got some yeses and some no's. Well, what did we just say about 3? Does 3 have a y value? When x is 3, do we have a y? No. So that means we're looking at everything from -5 to 6, but we have to exclude x equals 3. We actually don't have a defined point when x equals 3. So a couple of different ways that we could write this. We use our interval notation, -5 up to 3, but not including 3 because I don't have a point there. And then after 3, everything to 6 and including 6 because it's a closed circle. That would work. This as inequality notation would be -5 is less than or equal to x is less than 3 because I can't include 3. And then the other part of this would be 3 is less than x is less than or equal to 6. I have to break up at 3. You may also see something like, although this is my least favorite, and then you have to make a note that we exclude 3. I show you this because you will see problems where your domain goes forever one way and like forever another way, but there's one little gap. And so this would be something like all real numbers excluding x equals 2. Okay. If we have a discrete domain like we do here, though, this would be what I would expect to see from you. Either the interval or the inequality notation. This is more common for something where you're going to infinity and -infinity. Does our function have x-intercepts? Any x-intercepts here on your graph at -2? How about y-intercepts? Any y-intercepts here? At 2, at +2. I don't want you to forget the old stuff if we're working on new stuff. And then another thing we've done before, piecewise function that represents this. Okay, so my sort of left piece looks like a line. What's the slope on this line? 1. So 1x, and then we can see the y-intercept. So I'm going to write slope-intercept form. So I have a piece that's 1x plus 2. And that applies to that first part of my domain here, from -5. So this is essentially what I'm going to write down here, from -5 up to, but not including 3. And then after 3, this is just a horizontal line, right? Y equals 6. From 3 up to and including 6. On the next page, I want you to try example 3. Try example 3. Okay, let's take a look. F of -2. So when our x value is -2, our y value would be +2. F of -1, nothing on the top part of the graph, nothing on the bottom part of the graph. What I actually have here that we'll talk about in a little bit, it's called an asymptote. So something my graph will get really close to, but as we can see, I don't actually have a point there, I don't touch it. So I would say that this is undefined. I don't have a y value defined for that value of x. F of 0, I do have a defined value. F of 0 is equal to 0. And then at f of 2, we have an open circle. So again, no defined value there. I would again say that this is undefined. So when I give the domain, I have to make sure I exclude these pieces here. So I'm going to show you interval notation. This would go from -infinity, check your work as I'm writing, to -1. And then from -1 to 2. And then from 2 to infinity. Notice parentheses all the way. I can get very close to -1, but I cannot include -1. I can get very close to 2, but I cannot include 2. So I want parentheses there. This is an example where you might see all real values excluding -1 and +2. And then x-intercepts. Does our function have any x-intercepts? Do I have x-intercepts here? At 0. And then how about y-intercept? At the same place. Yep. Questions for me so far? Okay, so we talked about domain. Now let's talk about continuity. So the functions that we've looked at so far, okay, for examples 2 and 3, have not been what we call continuous. They are not continuous because they've had breaks in the graph of some point. Breaks, gaps, sort of splits in my functions. That makes them not continuous. For a function to be continuous, that means that I have a defined function. I can find a value of y for every value of x between any two values that I may choose. Okay, we don't have that here. We've got this sort of split in our graph here. We've got a hole here. That's not continuous. Back here, we've got this sort of jump or gap, this vertical gap. That's not continuous. If I go back to my earlier examples from today, D, also not continuous. We've got this big gap here. Those are not continuous functions. But something like A or B or C, those would be what we're talking about when we say continuous. Okay, for the defined part of that function, everything in between -11 and 11 is defined. Everything in between -6 and 11 is defined. From -infinity to 4, that's all defined. Okay, no gaps, no breaks, no jumps, nothing like that. Okay, discontinuous graphs, like what we've seen for several of our examples so far, can have multiple types of discontinuities and multiple discontinuities of the same type or of different types in our graph. So for example 3, this is an example of a graph that has 2 different types of discontinuities. We have this sort of split in my graph here. We've got a hole over here. Those are 2 different discontinuities. Okay, discontinuities we can classify by their type. If I have a 1 point that is missing, we call that a removable discontinuity or a hole. So this would be a removable discontinuity or a hole. I am going to use hole more than I use removable discontinuity because hole is only 4 letters and removable discontinuity takes a lot longer to write, but they mean the same thing. Okay. So there's our hole. This sort of split in our graph is a vertical asymptote. When I have a vertical asymptote, my graph can approach infinity, opposite infinities, I should say, or the y. They could go towards the same infinity, but not be continuous. So you could also see something that looked like this, where on both sections of my graph, we're going the same direction, but it's not continuous there. That's also a vertical asymptote. And then the last one we'll see is where I have what kind of looks like a piecewise function that's just not connected at that piece. So I'm coming in from one direction, and then on one end, we have an open circle, and then we have a vertical gap. And then it could be a filled in circle or another open circle for that next piece of my function. That's what we call a jump discontinuity. So those are the 3 types that we'll talk about, that we'll see. So for our next example, we have a graph here with several types of discontinuities. Okay. We're going to talk about what each of them are. So at -2, I have a gap between as I move from left to right, where my function value I expect it to be and where it actually is. So this type of vertical gap we call a jump. That's a jump discontinuity. This is different from a hole because that point is defined somewhere, but not where I expect it to be. At x equals 0, we have a hole. This is a hole because that value is missing entirely from the domain. It's not defined elsewhere, it is just gone. Does that difference make sense? Why this is the jump, but this is just a hole? Okay. And then at 5, that's an asymptote. Asymptotes are usually pretty easy to identify. That is a vertical asymptote. We need to make sure we include vertical because there are other types of asymptotes, but those types of asymptotes wouldn't necessarily impact our domain. Vertical asymptotes absolutely impact the domain because it's an x value where your function is undefined. So you do need to include the word vertical there. On the next page, another graph. Okay. Where do I have discontinuities here? For what values of x is my graph discontinuous? Mm-hmm. When x equals 4, what do we have it for? A hole. And where else? Somebody I haven't heard from yet today. Mm-hmm. At -3. What do we have at -3? We have a vertical asymptote at -3. So in B, when I ask you to evaluate, you can find f of 1. F of 1 would be -3. You can find f of 9. F of 9 would be -6. But f of 4 is the place where our graph is discontinuous. So at f of 4, because it's a hole, okay, we would have to say this is undefined. Now, I want to point out something. For holes and vertical asymptotes, our graph is undefined at those places. But for jump discontinuities, like at -2 here on our last example, we're not undefined there. Okay, the graph is not undefined when x equals -2. When x equals -2, we have a point there. It's just not where we expect it to be based on the rest of the function around it. Okay, so I would be able to find f of -2 for this graph. F of -2 would be 1. That's a difference. Okay, if it's a jump discontinuity, it is not necessarily undefined. It could be still, but not necessarily. So then if I state the domain of this guy using interval notation, I would like you to do that for me now. Using interval notation, give me the domain. You should have -9, including -9, so a bracket there. We include -9. up to -3, but a parenthesis on -3, because I cannot include -3 in the domain. And then our next piece, so that's this piece we just wrote, our next piece will go from -3 until 4. Parentheses on both ends, because I do not have -3 or 4 in the domain. Those are my discontinuities. And then the last section of my graph starts when x is 4 and goes until x is 9. So from 4 until 9. 9 gets a bracket because we do have a closed circle there. Check your domain. We have all 3 intervals. Try example 6 on the next page. We were doing all of example 6. Be careful when you give your domain for example 6. Okay, discontinuities. Where do I have some discontinuities here in this graph? When x equals, when x equals -7, we have a discontinuity. What kind of discontinuity? I can see why you would say whole. You see how we have a vertical jump there? Vertical gap. If we have a vertical gap where I said jump a second ago, we usually call that a jump. But I definitely see where we would say whole because I don't have a defined value for that. I have another location on this graph where I have a discontinuity. Where's my other discontinuity? -3. How about -3? So this one, we would say vertical gap. We would call that a jump. Just like, where did we have? At -2, right? For example 4, there was a hole in the graph, but it was defined somewhere else. That's a jump. Okay. Jump is anytime I'm chugging along and then very abruptly my graph moves to a different spot vertically. That's a jump. So that's why we would call this guy a jump, because I'm moving along and then all of a sudden I have a big vertical change, and then moving along and all of a sudden I have a vertical change. Those are jumps. What's f of 9? -9, sorry. What's f of -9? 1. What's f of -7? Undefined. What's f of -3? 4. What's f of 4? F of 4. Oh, f of -3. It should be f of -3 is 3. There we go. F of 4. There we go. 6. F of -3, we have a discontinuity there, but that value is still defined. Okay, that's why I said be careful when you give your domain for the last part. Do I need to exclude -3 from the domain? No, I have a y value when x is -3. So my domain here in interval notation would be -9, including -9, up to -7, but not including -7, because I don't have a defined value at -7. And then -7 to +9, including +9. We don't need to skip -3 because I do have a defined value at -3. Questions for me for today? Okay. This is going to be what we're working with all week. Okay, so the next few days, we're going to be working on domain and continuity. You have a Delta math assignment for homework for tonight that's going to ask you about domain for functions and continuity for functions.